exciting year where some of our teaching is changing. The poster that was sent to you stated, the math hasn't changed. There is no such thing as fuzzy math or hard math. How we're going about teaching it so that kids understand it is changing and should change. We know so much more about the brain now. We know from our past experiences that math needed to change. Because honestly, I'd like to talk to you. How many of you, when you got to the part of fractions, were just jumping up and down out of your seat going, yay, this is my favorite part? There we go. But there's always one great person. There is a professor out of UC Berkeley in California, University of California, Berkeley, who's just published a piece saying that the math phobia in the United States, he says, can be tracked right back to fractions. There's another lady, Jo Boaler, out of Stanford. I am from California, but these two people just happen to be from California, who says it goes back to timed fat tests. These are things we are trying to change. We know that kids need to know their math facts, but there's gentler, kinder, and better ways of memorizing them. And we also need to know that they need to understand fractions and not panic when they see them. You're parents of 5th graders. This is not going to be a cohesive lesson of everything to do with fractions. I'm going to teach you 4 different areas today. They're not going to be one leading to the next to the next. This is a 7-week unit in 5th grade, and you're getting 45, 50 minutes of it. So we're going to look at these things. What I've done is I've picked out highlights that your kids and you should understand. And then the next one we may be skipping to something. I'm also putting it into real world contexts because I was a 5th grade teacher last year. I gave the fractions test and the kids said, well, I know it says multiply and divide, but I really don't know which is which. If we don't give the context, we don't know when to do it. And when I'm walking down or at a pizza parlor, nobody is giving me the fraction equation. I have to know how to put it together myself. So we're going to start with, the first page is understanding that fractions are actually in a different notation for division. And I want us to take a look at it. What I'm providing you with is we are all going to do the same work together. That way when you go home, you have a reference piece if your child comes and asks a question. So if we look at this, I want to make sure fractions are all about knowing what the whole is. In 3rd grade, in a few weeks, they're going to be asked a question. Do you want 1/4 of a cookie or do you want 1/8 of a cookie? Most of us would right off say, I want 1/4 of the cookie. It's a larger piece. But what if the cookie was this big around and you get 1/8? And what if the other cookie was this big around and you get 1/4? In fractions, we have to know what the whole is to make a good decision. So we have all these bars. We're going to start labeling them. I want to mention, this type of visual or representation is now being called the tape diagram. It is some new language. I wish mathematicians would quit changing the names of things. But the reality is I kind of feel like it's selling new cars. This is what they do. It's also having a more worldwide perspective, and that may be deciding, well, actually, another group of people was using this diagram and it makes more sense. So we are now, I used to call this the bar model. That language came out of Singapore math. The Common Core in the United States and the international groups that are using Common Core are really switching to the term tape diagram. Okay, what I want to show to you and have you believe that 1/4 is the same as the division problem 1 divided by 4. So if I take a look at this diagram, this whole piece equals 1. So to prove that 1 divided by 4, I'm going to cut it into 4 pieces. And I want to know the value or the size of this piece. Well, if I look at it, I now took my 1, I divided it by 4, I look at the value or the size of this piece, and it equals 1/4. Maybe I picked a fancy fraction, maybe that's the only one that works that way. Probably not. If we take a look at the next one, this is 3. I need to know that this is 3 wholes. I want to divide this into 4 pieces. Personally, I can't look at this and just do it off the top of my head. So what am I going to do? I'm going to look at one of my pieces, and I'm going to divide it into the 4 parts. And I look at my second piece, and I'm going to divide it into 4 parts. I'm going to look at my last piece and divide it into 4 parts. How many of those little parts do we now have? 12, okay. I'm just going to keep that. I want to divide these among 4 people. Well, if I have 12 of these parts divided by 4, how many are they each going to get? 3. Okay, so let's find our parts. Here's 3. Here's 3. Here's 3. And here's 3. Did I divide it into 4 equal parts?
Yeah.
And how much did each one of those people get, if that was my story?
3.
They got 3, and their size is 3 out of the 4, or 3/4. We always go back to our 1 to determine the size. So they got 3 out of the 4 parts. So we can do it with drawing. I would like to convince you also with the algorithm that we're used to. I'm telling you that 3/4 is the same as 3 divided by 4. How many groups are there of 3 and 4? There are none. I have 3 left over. I have 3 out of my 4 groups, which equals 3/4. So we can draw it. We can do it by our algorithm. But once again, the fraction is now the same as a division problem, if we choose to think of it that way. So 2/3. We're saying that 2 is divided by 3. We need to label our tape diagram and make sure we know this is 2. How are we going to divide it into 3 parts? Yep, we're going to cut these into 3s. Now I can do it just by figuring out what are 3 equal parts. I can see them, and they equal 2/3. I can count them, 1, 2, 3, 4, 5, 6. I have 6/3. Dividing them among 3, each section would get 2.
So
Yes.
basically, the numerator becomes our whole, and then the denominator, the parts of the numerator.
Exactly.
This is very clear now.
Okay, it's very clear now. Would you please do the next one? And if it's not clear to you, find out what somebody else at your table is doing. I honestly didn't know that a fraction was a division problem until probably 5 years ago. It had never been presented to me that way. problem. Is a division problem end up as a fraction? If I take 21 and I divide it by 5, using an algorithm. Not sure if you guys are recognizing this algorithm. Your kids have been taught it for 2 years now. It's similar to what we did. What we do is we think of groups. How many groups of 5 are there in 21? Probably 4. That equals 20. I subtract, I have 1 left over. So what does that mean? I have 4 groups, which is 1/5. So let me compare that 4 and 1/5 to 21/5. Are they the same? They are. If we make our mixed number into a fraction, I have 5/5 plus 5/5 plus 5/5 plus 5/5. Each of those equals our 1 plus 1/5. So I have 5, 10, 15, 20. I have 21/5. So in reversing the problem, it still works. Okay, so this is fractions as division. It was the first concept your kids used. It's the way they're now using to simplify improper fractions to get them into mixed numbers, and they've moved on, or are moving on the process. I'd like you to take a look at the next page. This is probably a more real-life situation. Very rarely are we asked to prove that a fraction is division. However, we do take parts of groups all the time. So this is 1/6 of 24. Actually, I'm going to ask you to start with 1/3 of 6. Would you please take out 6 cubes and break them apart? Pardon me? No, this was a separate. This one was separate. It was separate, we just did it by numbers. They did this themselves. Yeah, and then I This was just showing the inverse of it's 50. Oh, okay, you did, oh, I'm sorry. I let you work on one and then I went to showing the inverse.
Yes. I'm all confused.
Okay.
I want to get it right.
So what's it going to be? We have 5 groups. There's 3 in each, so there's going to be 15 of those thirds, correct? And then I need to divide them into 3. So there are going to be 5 thirds in each of the groups. Thank you. And then I let you work on that, and then I just wanted to show you that the inverse was true also, that you could take a division problem and it becomes a fraction. Should have known. We need to know the right answer. You guys have to have faith in yourselves. Okay. If we have 6 of anything, we have 6 marbles, and we want to break them into groups, and we want 1/3 of them. I'm going to take my 6 marbles. I want them into groups, 3 different groups. How many are going to go in each one of those groups? I have 1/3, I have 2/3, I have, 1/3, 2/3, 3/3, or I have 2, 4, and 6. So our answer is 1/3 of 6 equals 2. Again, how many of us walk around with cubes in our pockets to solve these problems the rest of our life? We don't. We need to move on. We do a lot of these problems with your students before they move on, but I think we can. We're going to get to a way of drawing it. Again, I'm going to go back. We have to know what our whole is. if we want 1/6 of 24, what does this tape diagram, what's the value of it? It's 24. I'm going to label that. Mathematicians label so they know what they're doing. I want 1/6 of it. That means I have to break it apart into 6 groups. How many, what is the value of each one of those groups? Yeah, it's going to be 4 in each one of these. And my problem tells me I get one of them. So 1/6 of 24 equals, what does 2/6 of 24 equal? What does 5/6 of 24 equal? 20. So we've got a representation here where we can start figuring any of those things out. And it proves it. There are 32 students in a class. Of the class, 3/4 of the students bring their own lunches. How many students bring their lunches? What's our first label? What's our whole equal? 32. How many parts am I going to break this into? What's the value of each one of those parts? And it says 3/4 of them brought it. I'm going to circle it or hatch mark it. How many of those students brought their lunches? So 3/4 of 24, excuse me, of 32 equals 24. And along with this lesson, we're going to start talking to the kids about the language. 3/4 of 24 mathematically is written as 3/4 times 24. We do a lot of that. We explain the language. If we went back to whole numbers, which is where we would start, or
32, right?
excuse me. Making sure I note it right. You're going to need. So this idea that groups of groups is multiplication. 3 groups of 3 is 9. That is written as 3 times 9. We take it back to what they already know, then substitute in a fraction and see how it's the same. Learning off of something they already know is always preferable. And in fact, it's the real way. They're going to make the connection and actually learn it. So the next one, Abby spent 5/8 of her money and saved the rest. If she spent 45, how much money did she have at first? This is a different question. But we have the one model that works again. So this time, I don't know how much the whole is worth yet. That is actually the question. But I do know that she had groups of 8s. I know she spent 5 of them. Then it told me she spent $45. What do we know the value? What is the value of each of those units? Why is it 9? Because we have 5 of them that equal 45, so it would be 5 times what?
9.
So if these equal 9, how much money did she have at first? She had the 45, and she had 27 more. I know, I liked this one. So this is this tape diagram that really starts helping when we start asking our kids to do problem solving and showing their work. Of course, I don't have the final answer yet because it says how much do they have, so that would be 45 plus 27 equals $72 at first. Does that make sense? Would you and your table mates, let me see this one. Yeah, try the next one. Think about your labeling. And that's why we ask kids to label, because the label makes the problem solvable. We know they want 3/4. What do we know about 21? That's the fourth one. So what I'm saying is we knew that we could use our tape diagram, and it's into fourths. I'm going to label it. What do we know about 3/4? Nope, that's not what we know about 3/4.
They won.
We know that they won these 3/4. So, what's the last fourth? It's what they lost. What did it tell us? How many games did they lose?
21.
So if that fourth equals 21, what does this fourth equal? Okay, but I asked for one, but you gave me all three.
Can I ask something?
Yes.
Before it was not a tape diagram, but it was a bar diagram, right?
Same thing.
But that's how it is because this is the last
They
time.
lost one for
To be honest, at this school, I don't know how much the bar model is being used.
Okay.
But because I have it in grade 6 as well. And I have seen the tape diagram there, and I know how it's being worked, but I don't know if the last 5
I like the normal way, the old way. Yeah.
They've digested the concept.
Why do we have to learn the new way?
Are probably going to ask them to change the title. And I can apologize for it, but Common Core
My
has
son is by
chosen to
himself.
use
I can't do
this,
it.
this name.
Yeah.
The concept works the same. It's kind of like it's concept A or concept B, you know, and we feel it's our responsibility to shift to the new name because that's how it's starting to be used. I realize Common Core is the US, but a lot of the world is picking up on it also. So that's why we're shifting the language. The concept is there. We use it. Yeah, the concept is the same as the bar model, exactly. I know in 5th grade we used the bar model a lot. They were barely beginning to use it in 4th grade, so it's actually fairly new to them. But that's where we have, I talk to the middle school and tell them these are the differences that are occurring.
But now you use it in grade 3.
Now we're using tape diagram. Yes, we are trying to be consistent across the way. Absolutely, tape diagram starts probably in 1st grade. So now, hopefully, if my wish, they would leave the name alone. I know it'll be this way, I would guess for a good 10 years. Will something else come along? But again, we don't ask the kids to label that.
Confused than I came.
Yeah, it's the concept. It's this idea that you can take a model, you can take a rectangle, you can break it up into pieces and let them represent it. It's, for me, this model was significantly changed how we taught how to do problems because it works so often. It models so much. Okay, we're running a minute late. Shall we do the last one, or would you like to test it yourself at home? Do it, okay. We're gonna do speed. What do we know that it equals? It equals 30 cupcakes.
Yeah.
Spreads mint ice, oh, we need to do this one together. Spreads mint icing on 1/5 of the cupcakes. Okay? I can find 1/5. I know it's 6, and I'm going to label it mint. Whether it's labeled inside or outside, above or below, doesn't matter. The fact that it's labeled is important. Now I'm confused because I got 1/5, and then they say something about a half. My immediate brain says, but those don't go together real well. But it says chocolate, 1/2 of the remaining. So now I'm looking at these 4. Can I take 1/2 of those?
Yeah.
Absolutely. Here's my 1/2 of those 4. I know they're chocolate. And that would equal 12. The rest will get vanilla icing. Well, if each of these are worth 6, how many are left to get vanilla? If I looked at that and tried to write the equation for it, it would be way above 5th grade level. You give them the drawing of it, and they can figure it out.
They're smart kids.
In fact, I don't even want to think about how to write the equation.
I want to do
Okay, so we were taking a fraction of a whole number. What happens when we take a fraction of a fraction? You've got baggies at your desks or your tables. Could you take them out? And I have very, very mathematical terms for them. They're striped and they're dotted. Would you separate them into piles by stripes and dots? We're going to work this out logically before we go to equations.
They're gonna see.
And just like we do in class, I'm going to ask us to use stripes or dots. It doesn't change the math. It just helps us because we're beginners and our problem will look the same. Our first problem wants us to solve 1/2 of 1/3. Could you find 1/3 in your dots? So everybody can see we have we broke the rectangle into, and these are squares, I should be particular. 1/3, and we put dots in 1/3 of them. Would you look for 1/2 in your stripes? I'm being very particular about putting my dots horizontally. So I have 1/3 of a hole, and I have 1/2 of a hole. Is that easy to see? But I want 1/2 of this third. I now have my halves going the opposite direction. They're going vertically. If I put that over the top, I can see 1/2 of 1/3. Where it overlays or overlaps is 1/2 of 1/3. We can draw that. The big question with kids is, but what is the value of that overlapped area? Well, I have one of them. And what is my square now cut into? 6. 1/2 of 1/3 equals this area. don't usually do this, but if I just showed you 1/3 and said take half of it, we could do that, but we wouldn't know the size. I could look at it and I could say there it is, but I can't give you the fractional size. So that's why we need to know that it's half of the whole, then it's half of the third, and that tells me the size of that portion. And I'm going to go back and talk about our language. At this point with the students, we've talked a lot about it. It really does mean 1/2 times 1/3.
Exactly.
Exactly.
That's much easier.
Yes?
Okay, in the future, once they already learned that, you know, the method of like drawing as you did it, just.
Okay, can I
Okay.
let me pretend that I can read the future. Can you wait on that?
Okay.
So, I'm going to keep a column over here on the second or third day of math, because we've proven that 1/2 times 1/3 equals 1/6.
Yeah.
So I just got that up on the board. Okay, let's do 1/3 of 3/4. So I'm going to do 3/4 in my dots. And I want to multiply it by 1/3.
I'm more confused.
I have 1/3 of my whole. I want 1/3 of my 3/4. I guessed your question wrong, Ask.
Okay.
I'm pretty sure. Now, I was not picky which way I put those down. I had to have one of the fractions going horizontally and the other one going vertically, but I'm going to come up with the same answer. How many pieces do I have that are overlapped? 3. That's the definition of a denominator, the 3 pieces. Out of how many? 12. Okay? So I'm going to keep this piece of information up on the board. Let's do 2/3 times 2/5. At this point, I don't know if we have to take any apart. I wasn't really careful.
The final answer is 2/12,
Yes.
not 1/4.
It is 1/4. And we prefer it. There's times they're taking away the emphasis on simplifying fractions. We ask them to simplify it. It's a flexibility of understanding what numbers are and the equivalents. So we do ask them. But if a child got this far, we might give them 2 out of the 3 points. We wouldn't just mark it wrong. But if we didn't ask them to simplify it 3/12, it does equal 3/12. We encourage kids to simplify. Sometimes we make them simplify, sometimes we don't. They need the flexibility. They need to understand to simplify because that's used in algebra, and it's used both ways in simplifying stuff. So in this unit, they're probably going to be encouraged to do 1/4. The reason I'm not doing it now is because I'm going to answer the previous question. Okay, so we have 2/3. I got started. Times 2/5. I'm going to show it even a different way with the 2/3 at the top, the 2/5 on the right-hand side. It doesn't matter. I still have the same 4 pieces shaded out of 15.
Yes.
Now, these may seem like the word esoteric, but actually we do this in real life. So if we said Santino bought a 3/4 pound bag of chocolate chips and he used 2/3 of the bag while baking, how many pounds of chocolate chips did he use while baking? That's actually a fairly real life one that a strange math book writer didn't have to pull out of thin air. It's something that could happen in life. So could you solve the last one? some things apart. Or we could move to drawing it, actually. Okay, did you get 6/12?
Yes.
Okay. Your students, your children will be using these, but they're not going to be given them. So we do move them over to drawing it, but really once you've used these as manipulatives, the drawing comes fairly early. When we get into the drawing it, we do highlight that they start labeling. Just like I said earlier, we need to know what the parts are. So I labeled my last one. But it's 5th grade. We've collected these problems. In my classroom, I would have the kids sitting at the whiteboard saying, what pattern do you notice?
Basically multiplying numerators and denominators.
Well, that worked on 1/6, so you're saying that 1 times 1 is 1 and 2 times 3 is 6. Did that work on the first one? I would probably present them one at a time and say, yes, but I picked a very special case. What about the next one? They have their proof from doing them, from building them and drawing them. Does it work every single time? 1 times 3 equals 3, 3 times 4 equals 12.
Yes.
2 times 2 equals 4, 3 times 5 equals 15. We can go on forever. It will work every single